Hello, my name is Simon Flores, and today we'll be going over Carbidopa, which is also sold under the trade name Lodocine, and pretty much this drug or prodrug is used to inhibit a certain enzyme, which we'll be talking about further or more in depth here in a second. But a little bit of background on this drug and how it affects. We can go to the next, and it's used for treatment for Parkinson's disease, and so what exactly does it do? So dopa, the carboxylase, is responsible for the synthesis of key neurotransmitters, which are dopamine and serotonin, which they're done via the carboxylation of L-3,4-dihydroxyphenylalanine, which is also known as L-dopa, and L5-hydroxytryptophan. And here we can see on the PowerPoint we can see the process of it. And right here, this is where our carbidopa comes in. So this is where it comes in, and this is the inhibiting enzyme, which stops the aromatic amino acid decarboxylase to turn that levodopa into dopamine. So why would we want to do that if it's needed for brain function? We'll be going over that here in a second. But on this other graph, so yes, we are stopping it from going, converting this levodopa into dopamine, but it's in other places. So meaning if we stop this process everywhere else except for the brain, so all of this excess L-dopa is sent to the brain, which is where it is transmitted, where it is converted into dopamine, as we can see here. The L-dopa is then converted into dopamine, and it can be used for dopamine receptors, and it's distributed from there in the brain. So again, it stops it elsewhere, so it can be readily transportable to the brain. A little bit of background on the X-ray crystallography. So first, you have your X-ray, which is an arrow beam of X-ray, and it's directed at a well-ordered crystal. And this crystal is your protein crystal. And you shoot this crystal with your X-ray, and this is where your diffraction spots occur. So the atoms in the crystal scatter some of the beam, and again, this is where your diffraction spots are formed, and that's where you start getting this image from all these diffraction spots. And from this image, you can obviously start building your atomic model, which could be a 3D structure. As you can see, that's the last step here. So you go from your X-ray beam, shoot it to your crystal protein, you get your diffraction spots, you get your image here, and then you can build on that to get your 3D structure. So a little bit on the structure of carbidopa. Again, we already know it's used to inhibit this the enzyme which produces dopamine. So now we can go over the different structures and how it's pretty much the bound structure of it. And here we can see that's Carbidopa. So a little bit on the primary structure. Each of the polypeptide chains of this dopa decarboxylase is composed of 486 amino acids that eventually encode the three-dimensional structure of the protein. For our secondary structure, these elements, they start forming alpha helices and beta sheets, which you can also see here on this structure. And these are given due to, obviously, we talked earlier about our hydrophobic effects and how they neutralize these main chain polar groups by hydrogen bonding. And each polypeptide chain is of dopa decarboxylase is composed of 7 stranded mixed beta sheets and 4 stranded anti-parallel beta sheets and several alpha helices, among other lesser known structures. And now to talk a little bit more about the tertiary structure. And right here we're talking about pretty much the overall, I guess, polypeptide chain that it creates. And if we look at this, we have 3 different domains that are created for the tertiary structure. So first we have our large domain, which contains the POP binding site, and this consists of 7 stranded mixed beta sheets that is surrounded by 8 alpha helices. Then you have your C-terminal domain. Obviously, you have your C and your N-terminal domains. But right now, we're going to talk about your C-terminal domain. And it's composed of 4 stranded anti-parallel beta sheets that have 3 alpha helices packed against the face of the opposite of that large domain. And now for our N-terminal domain, it's pretty different than the others, as there's something that's called domain swapping. So on this one, the domain is composed of 2 parallel helices linked by an extended strand, which is pretty much like a flap over of that second subunit. And that's a little bit of background on that bond structure of Carbidopa. Thanks for watching.